we have simple harmonic motion whenever the acceleration is proportional to the displacement and it is in the opposite direction. So the acceleration is proportional to the displacement in the opposite direction. We can formalise this a little bit better though, because at the moment that k could be negative. So I'm going to formalise this to overcome the fact that that k could be negative and then the two negatives cancel out and overcome this. To stop that from happening, instead of writing k here, I could write omega squared. You could write k squared if you wanted to, but we tend to use omega in this topic. The key thing here is this is the constant, the proportional constant, and by making it squared, that ensures that this is definitely positive, which means that the acceleration will definitely be in the opposite direction to the displacement there. Now, the acceleration, I know that that is the second derivative of x of the displacement with respect to time, which I could write even shorter as just x dot dot. So this is my equation for simple harmonic motion. Before we go into the examples of this, just quickly, I could write this in a slightly different way, because I also know that the acceleration can be written as the rate of change of the velocity with respect to time. And by the chain rule, I know that dv by dt is the same thing as dv by dx times dx by dt, because you can see these cancel out. And dx by dt, I know that's the same thing as the velocity. So therefore, instead of writing the acceleration here, I could write dv by dx times the velocity. And that's a slightly different way of me writing the equation for simple harmonic motion. Most of the time it is written like this, however, because that gives us our definition. Right, let's have a look at simple harmonic motion in a little bit more detail. So I'm going to try and show you the two main examples that we come across, which are a mass on a spring, and then in a minute we'll do pendulum. So it is related to circular motion as well. You should, by the way, have done simple harmonic motion in your physics, but you won't have done it in as much mathematical detail as we're going to do it. So we don't need to worry about the circular motion. All we need to worry about is the mass on the spring and how that gives us this equation and the graph. So what we have here is a mass that's been attached to a spring, and it has been pulled a distance away from its original position, x equals 0. So that was its original position, and it's been pulled to a displacement of x. So obviously at the moment here, this spring is stretched, and so we know that there's going to be a restoring force. The spring is going to be pulling the object back towards the original position here. So the force is going to be in the opposite direction to the displacement here. It's been pulled in this direction, but the spring force is going to be acting to pull it back in the opposite direction, hence the negative. So what we're going to see here, let me just run the animation. So you can see the object is going to be pulled backwards. At this point over here, the spring is now compressed, so the spring is now going to be pushing the ball back in the opposite direction here, again in the opposite to the displacement when it's over here. So I'll just run that again so we can see the whole cycle of motion. Right, so what we can see it's given, we'll see where this equation comes from in a moment. We'll derive this for ourselves in a moment. But I just want to show you what happens when we change that omega there. So as I increase the value of omega, we can see the graph has moved, has been enlarged by a scale factor of by a scale factor of 1 over omega. We can see the period of oscillation is decreased. If we run that, we can see the object is moving quicker now. We'll come back to that in a little while. Right, so that's the displacement graph. I just want to show you the velocity graph. And so there's the velocity graph. You can see that this is, if I were to differentiate the omega, let's go back. If I were to differentiate this to get the velocity, I would get cos differentiates to minus sine times by the omega by the chain rule. So we get minus omega a sine omega t. And again, if I just run that oscillation, run the simulation. So this is giving us our velocity. And I'm going to show you the acceleration as well. So if we were to differentiate the velocity function I showed you a moment ago, differentiate that again, I get this expression. And key thing here, you can see the acceleration is in the opposite direction to the displacement. So when our displacement is x in this direction, you can see the acceleration is in that direction by this arrow here. Then the acceleration switches now. The acceleration direction switches each time we go through the origin position here. So this is the motion for a mass on a spring. I'm going to show you a pendulum as well, because that's the second example, really common example that we look at with simple harmonic motion. So I've got a pendulum here. In this case, it's obviously not a, we'll just go through once. It's obviously not a, it's not the spring that's causing the simple harmonic motion here. In this case here, it's a combination of the tension in the string. Let me pause it. That's already paused. It's a combination of the weight acting vertically downwards, of the weight of the ball on the end of the string, pulling it downwards, but also the tension in the string, pulling it at an angle up to the pivot point there. So you've got a combination of the weight downwards and the tension at a slight angle, which is then producing the force which is in the opposite direction to the displacement from that equilibrium, from that origin position. So that's what's causing the simple harmonic motion here. And again, we've got a graph of the acceleration versus time here. And hopefully you can see as I play it again. Oh. There we go. You can see how the acceleration is always in the opposite direction. So you can see here when the displacement is over here and being positive, the acceleration is at its maximum being negative down here. When we are at our equilibrium position there, so the displacement is 0, you can see the acceleration is 0 as well. Anyway, I'll put the links to both of these animations into the channel so you can have a play around with those yourselves. But most importantly now, I want to go through the maths of how we can get to those equations that model these situations. So starting with the definition of simple harmonic motion, we've got this is a second order differential equation. So I'm going to rewrite, because I want to solve this differential equation, so I'm going to rewrite the x dot dot as the second derivative of x with respect to t, and I'm going to move the omega squared t to the left hand side. Then I'm going to find the auxiliary equation for this. So the auxiliary equation for this is going to be m squared plus omega squared. Solve the auxiliary equation. So the two solutions of this are omega I and minus omega I, which means that I can write down a general solution to this like that. Now we know from our regular A-level maths, going back to the work we did on advanced trigonometry, we can rewrite a combination of cos and sine using the r cos alpha or r sine alpha. You could do this r sine omega t plus alpha as well. Remember, we could do it either way, but we can rewrite this as a combination of cos. We could rewrite this combination of cos and sine as a single trigonometric function, which just makes it easier to understand when we do that, because you've got one function varying rather than two functions varying. So we can go through the maths and rewrite this like this. And the advantage of doing that is that we can now draw the graph of this more easily. And depending on the different constants, depending on r, omega, and alpha, they each tell us different pieces of information. So let's go through each of those pieces of information. So I'm going to start off by assuming, let's just assume that this alpha is 0 to begin with, just to keep things simple. That then gives us actually the original, I'll just come back over here. There we go. So you see here we've got the x equals a cos omega t. So if alpha is 0, then this is now, I've shown you where this comes from now. The only difference is they've used a instead of r. So if that is 0, so let's draw the graph of that. It'll look like that, the cos graph. So the cos graph starts at r and is going to go down to minus r. So this r here is representing the amplitude of the oscillation. It's talking about the maximum displacement. The alpha, what that's doing is that's controlling the starting position, because this is going to represent a translation in the x direction. So for example, if alpha was not 0, it might mean that actually it didn't start at its maximum amplitude. Here I'm saying that when t is 0, the displacement is at its maximum. So it's starting furthest away from the origin position. But it doesn't have to be. Could start here and then move out to its amplitude position and then back in. So this alpha here is controlling the starting position. The omega, like we saw in the simulation, is controlling the time period. So how quickly it takes. The bigger omega is, the shorter the time period. So here, in this case here, I'm just assuming that omega is 1, because I'm saying that one period takes 2 pi. If omega was not 1, then our time period would be given by 2 pi over omega. So the time period is 2 pi over omega. If this was 2, then the time period would be pi. If this was 4, then the time period would be pi over 2, and so on. So that's where the general equation comes from and what each of these things represents. This is controlling the amplitude, this is controlling the time period, this is controlling the original displacement. Let's now look at a specific example. So let's actually put some numbers in and solve this. So we are told that a particle is moving along a straight line. Its motion can be modelled by the equation d2x by dt squared equals minus 4x. So we can see here that this is going to be simple harmonic motion, because the acceleration is proportional to the displacement in the opposite direction. We're told initially, so I know that t equals 0, its displacement from the origin is 1 metre, so x equals 1, and its velocity is 4. So these are my boundary conditions. When t is 0, x equals 1 and v equals 4. Part A finds an expression for the displacement after t seconds. Part B, hence find its maximum displacement or its amplitude. Maximum displacement, same thing as amplitude. And part C states the period of the motion. Okay, so part A finds the expression for the displacement. So I want to solve this differential equation to get x equals something. So start off like we always do when we solve differential equations. I want to get second order differential equations anyway. I want to get the auxiliary equation. I find the two values of m, which are going to be plus or minus 2i, which tells me my solution is going to look like that. I want to know the value of a and b. So I'm going to use the boundary conditions here. Remember, I know that when t is 0, x equals 1 and v equals 4. So if I use the boundary conditions, so let's use the first one. When t is 0, x is 1. So if I substitute 1, 0, 0, I get that. I know that sine 0 is 0. I know that cos 0 is 1. So that's 1 equals a. So a is 1. So I know that so far, just replacing the a with 1 here. Now to work out b, I'm going to use the second boundary condition. So the velocity is 4 when the time is 0. So in order to use the velocity, I need to differentiate this to get a dx by dt. Oops. So if I differentiate this, I get this. If I differentiate this, I get this. Substitute in 4, 0, 0. I get this. Again, I know that's going to be 0 here because sine 0 is 0. I know cos 0 is 1. So 2b equals 4, so b is 2. So I now have replaced the 1 here and the 2 here. And this is my answer to part A. This is my general equation for displacement after t seconds. Part B, hence find its maximum displacement. So we saw before that in order to get a maximum displacement, I'd like to have it in the form where I've got either r cos, blah, 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 or r sine, blah, blah, blah. One of those two things. So I'm going to need to use the techniques from regular A-level maths now. So I've chosen to do it in the r cos form. You could do it in the r sine form, absolutely fine, you'll get the same answer either way. So you can see I put a minus in the middle here because obviously if I'm doing the cos, then I know that when I expand the minus out, that will give me a plus in the middle like I wanted to. If I put that as a plus, if I said that as a plus, then that would have had to have been a minus, and I'm making it more complicated for myself. So because that was a plus, I knew that had to be a minus there. Expanding this out, so I've got r cos 2t cos alpha plus r sine 2t sine alpha. Comparing them, got a cos 2t there, a cos 2t there, which means that r cos alpha is going to be equal 1. I've got a sine 2t here, a sine 2t here, which means that r sine alpha is going to equal 2. Just dividing both of those by r, just so I can draw my nice right angle triangle. So I can see that the adjacent over the hypotenuse is cos alpha, the opposite over the hypotenuse is sine alpha, so that gives me this. So r, doing a bit of Pythagoras, r is root 5, tan opposite over adjacent, so tan alpha is 2. Do tan inverse of 2, I get 1.11. Obviously this has to be in radians here, not in degrees. It has to be in radians for within calculus. So I can now rewrite my original equation in this form, which is useful because that tells me that the amplitude is root 5. Remember this here is representing the starting position, because And that should hopefully make sense, because initially its displacement from O was 1 metre. 1 metre is not the amplitude as we've seen here, so it's not starting from the origin, it's not starting from a maximum displacement, it's just starting at a random position, 1 metre, hence why this is not 0. We've got some correction factor here. This is representing like the translation of the graph. The 2 here, that's our omega. Omega is 2. Therefore our time period then will be 2 pi divided by 2, which is pi, so 3.14. So it's got a maximum amplitude of √5, so 2 point something or other meters, and it takes 3.14 seconds to do one oscillation. There we go.